Assalamualaikum and hi, my name is Nusharfa Amni binti Sayuti. Imagine you're a banana farmer in Perak and your livelihood depends on two simple decisions, which is how much fertilizer should I add and how much water should I use. So get it right and you will harvest record-breaking yields. Get it wrong and you will waste money, harm your crops or even face crop failure. But here's the good news. Today, we'll solve this problem using a derivatives of multivariable functions to find the perfect balance. Let me clearly state the problem we are addressing today. Banana cultivation in Perak requires careful management of two key inputs. First, nitrogen fertilizer, where it's essential for plant growth but harmful in excess. And second, water irrigation, which is critical for plant health but wasteful if over-applied. The core challenge is when applying too much nitrogen will burn roots and reduce yield, and using too little water will stress the plants and limits production. But these factors will interact in complex way, and our specific optimization problems is to determine the exact amount of nitrogen in kilogram per hectare and the precise water application in millimeter per hectare. That will maximize banana yield while avoiding plant damage from over-fertilization and preventing water stress or waste. That is fundamentally a problem of finding the optimal point of multivariable function, which is exactly what calculus helps us solve. To tackle this, we will apply partial derivatives to the banana yield function, which I will show you next. At the heart of our optimization problem lies the banana yield function, which is 50x plus 40y minus 0.5x squared minus 0.3y squared plus 0.2xy. Here, the variable x represents nitrogen and y represents water. This mathematical model allows us to predict exactly how nitrogen and water inputs will affect crop production. The function has three key components that each tell an important story, which is, in the linear term, 50x plus 40y represent the baseline productivity. Here, we can see that each kilogram of nitrogen will contribute 50 yield units and each millimeter of water will add 40 yield units. This is the positive and proportional relationship that we expect. And second, the quadratic terms, which is negative 0.5x squared and negative 0.3y squared, will reveal the diminishing returns. At 10 kg per hectare of nitrogen, we will lose 50 yield units from over-application, and at 10 millimeters per hectare of water, we will lose 30 yield units from excess. This term model are the real-world toxicity effect. Next is the interaction term, which what we call the teamwork bonus. The equation plus 0.2xy tell us that nitrogen and water work better together than they do alone. For example, if both nitrogen and water are at the 10 units, we get 0.2 times 10 times 10, which gives us 20 extra units of banana yield just from the synergy between the two. Why does this happen? Because plants need water to absorb nitrogen efficiently. Without water, much of the nitrogen will go to waste. So, applying 10 kilograms of nitrogen with 10 liters of water will give us much more yield than nitrogen alone. That's the power of coordination, and this term will capture it beautifully in our model. Let's look at how to find the critical points of our banana yield function. Step 1 is to compute the first partial derivatives, that is how the yield changes with respect to nitrogen and water. The partial derivative of b with respect to x is 50 minus x plus 0.2y. The partial derivative of b with respect to y is 40 minus 0.6y plus 0.2x. To find the critical points, we will set both of these derivatives to 0, which is in the equation 1, 50 minus x plus 0.2y equals to 0, and equation 2, which is 40 minus 0.6y plus 0.2x equal to 0. We now have a system of equations that we can solve to find the optimal values of nitrogen and water that maximize the banana yield. To determine the optimal levels of nitrogen and water, we now solve the system of partial derivatives we found earlier. First, we substitute equation 3 into the water equation. That gives us 50 minus 0.56y equals 0. Now, we solve for y. That will give us y is approximately 89.29 millimeters per hectare. And now, we substitute the value of y back into the nitrogen equation to find x, and that will give us x is approximately 67.86 kg per hectare. So, our critical point is 67.86 for nitrogen and 89.29 for water. It is our candidate for maximum banana yield. Next, we will verify whether this point actually gives us the maximum yield or minimum yield or even a saddle point. Next, to verify if our critical point is maximum, minimum or saddle point, we will perform second partial derivatives. In a point B sub xx, the rate of change for nitrogen effect decreases consistently, where B sub xx is equal to -1. This means yield gains slow as we add more nitrogen, and it's like pushing a boulder uphill that gets heavier. And next is point 2 B sub yy, which is similarly for water. B sub yy is equal -0.6, which is showing diminishing returns. Similarly, water shows diminishing returns, which is -0.6, though less severe than nitrogen. And next, point B sub xy, where the cross derivative 0.2 confirms their positive interaction. The positive interaction terms 0.2 confirms this input works together, which water will help plants utilize nitrogen more effectively. And next, we will organize this into Hessian matrix, which is a mathematical snapshot of the yield surface curvature at our critical point. The negative diagonal entries, -1 and -0.6, tell us that the yield curve bends downward in both directions, like standing on a hilltop, where the diagonal 0.2 values are the positive interaction terms, which shows nitrogen and water that amplify each other effect, but it is not enough to create a saddle shape. Next, let's calculate the discriminant based on the formula using our second partial derivatives, which will give you the total equal to 0.56. Next, we will interpret the result by looking at this statement. When D are more than 0, we have two clear possibilities, which is if B sub xx are less than 0, we have found a local maximum, which is our yield peak. And if B sub xx are more than 0, it will be a local minimum, which is the worst case. And if D are less than 0, we have a saddle point, which are unstable for farming. So, for our result, and our verification, D is equal to 0.56, which is more than 0, and our B sub xx are -1, which is less than 0. So, this gives us the proof that 67.86 and 89 this gives us proof that 67.86, 89.29 is indeed the optimal point for the maximum yield. And with this verification complete, we can be 100% confident that 67.9 kg per hectare nitrogen and 89.3 mm per hectare water, which will represent the scientifically validated optimal input combination. I will state the maximum and minimum point of this issue. The maximum point is 67.86, 89.29, where the minimum point is in agriculture, input XY cannot be negative. So, the minimum banana yield occurs at 0 input, which is 0, 0. So, when there is no fertilizer and no water, there is no harvest. This 3D graph visually demonstrates how nitrogen and water inputs affect banana yield with the function 50x plus 40y minus 0.5x squared minus 0.3y squared plus 0.2xy. The x-axis displays nitrogen fertilizer from 0 to 100 kg per hectare, while the y-axis shows water irrigation from 0 to 100 mm per hectare. The height of the surface represents the resulting banana yield in kilogram per hectare. The graph reveals several important patterns. First, we see a clear peak yield point at precisely 67.86 kg of nitrogen and 89.29 mm of water per hectare, where the maximum yield of 3,481.5 kg per hectare is achieved. This represents the mathematically proven optimal input combination. The surface shows a concave shape, demonstrating that the yield initially increased as we add more inputs, but then decreased after passing the optimal point. This matched our understanding of real-world effects like nitrogen burn and waterlogging that occur with over-application. The most dramatic yield reductions appear at the graph edges when nitrogen approached 100 kg with little water, or when water approached 100 mm with little nitrogen, yields drop sharply towards zero. This extreme imbalance demonstrates how improper input ratios can be disastrous for production. At the opposite extreme, the minimum yield occurs at the origin point 00, where no inputs are applied, confirming that both nitrogen and water are essential for any meaningful production. What this means for farmer is clear. By targeting 67.9 kg per hectare nitrogen and 89.3 mm per hectare water, they will achieve maximum production while avoiding the substantial losses that come from guesswork or improper ratios. Next, let me explain what this partial derivative tells us about nitrogen effect on banana yield. This equation, which is the partial derivative of b with respect to x, equals 50 minus x plus 0.2y, it mathematically describes how banana yield changes when we adjust nitrogen levels while keeping water constant. When we examine the graph of this function, we see three crucial scenarios. First, when the slope is positive, which is greater than 0, increasing nitrogen leads to higher yields. This occurs when nitrogen levels are below the optimal point. Each additional kilogram will boost the production. Second, when the slope equals exactly 0, we have reached maximum efficiency for nitrogen use. At this precise point, adding more nitrogen provides no additional yield benefits. This represents the optimal nitrogen level for any given water amount. Third, when the slope becomes negative, which is less than 0, we have entered the danger zone. Here, excess nitrogen actually reduces overall yield, which the plants are being harmed by over-fertilization. The 0.2y term in the equation reveals an important interaction. The optimal nitrogen level increases slightly when more water is available, as water helps plants utilize nitrogen more efficiently. This relationship proves that blindly adding more nitrogen doesn't guarantee better results. This graph shows how banana yield responds to changes in water application when nitrogen levels are held constant. The relationship is described by the partial derivative of b with respect to y, which equals 40 minus 0.6y plus 0.2x. The graph reveals three important scenarios. First, when the derivative is greater than 0, increasing water improves banana yield. This means the plant can effectively use additional water when they are below the optimal amount. Second, when the derivative equals exactly 0, we have reached the point of maximum yield efficiency of water. At this stage, adding more water provides no additional benefit to the plant. Third, when the derivative becomes less than 0, we see the negative effects of overwatering. In this zone, excess water actually harms the crop and reduces overall yield. The term 0.2 times x in the equation shows how nitrogen affects water needs. When more nitrogen is available, the optimal water level increases slightly because well-nourished plants can utilize more water effectively. This graph proves that water application follows the same principle of diminishing returns as nitrogen. There's a precise optimal level where yield peaks, and going beyond that point leads to decreasing return. So, The mathematical relationship helps us calculate exactly where the optimal point lies for any given nitrogen level. Next, our analysis has determined the precise optimal inputs for banana cultivation, which nitrogen are approximately 67.86 kg per hectare and water are approximately 89.29 millimeters per hectare. When we plug this value into our yield function and calculate the maximum predicted yield, we will get approximately 3,481.5 kg per hectare. Why this number matter? Exceeding 67.86 kg of nitrogen per hectare will actually reduce your yield due to fertilizer burn, and applying more than 89.29 millimeters of water will lead to waterlogging and nutrient leaching. The positive interaction terms, which is 0.2xy, means this input work together, which means proper irrigation makes your fertilizer more effective and proper fertilization helps plants use water more efficiently. And for recommendation, for maximum banana yield of 3,481.5 kg per hectare while avoiding resource waste, apply exactly 7.86 kg of nitrogen per hectare and irrigate with exactly 89.29 millimeters of water per hectare. This mathematically proven combination ensures optimal plant health and productivity. In conclusion, for farmers in Perak to achieve the highest banana yield and prevent resource waste or crop damage, apply approximately 67.86 kg per hectare of nitrogen and provide approximately 89.29 mm per hectare of water. This strategy ensures healthy growth, maximizes profit, and supports sustainable farming. That's all from me. Thank you.